So metric spaces are spaces with distances, and they are the ones that provide the largest class of interesting and important examples of topological spaces. I don't just mean examples. A large part of studying topology is specifically studying the topology of metric spaces. In fact, we have to justify, as we do later, why we don't just stick to metric spaces. So a metric space is a set. So it's a set with a distance function. So it's a set X with a function which is going d, which will take x product x to r greater than or equal to 0, non-negative real numbers, which is the set of all x in R such that x is greater than or equal to 0, which satisfies the properties you expect of a distance. So first of all, what is the distance is to be non-negative, but it's 0 exactly when 2 points are equal. So the distance between a point and itself is 0, but the distance between different points is not 0, it's positive. Secondly, it's symmetric. Distance between xy is distance between y, x, and let's put quantifiers for all x, y in x, and again here for all x, y in x. And the third property, which is in some sense the key, is the what is called the triangle inequality. This time for 3 points, we have, if I look at distance between x, y plus distance between y and z, this is greater than or equal to distance between x and z. For all x, y, z belongs to the space. Okay. So the last property is called the triangle inequality. And that is the key property of metric spaces. In fact, we can in some sense repair things if they don't have 1 and 2. If they don't have 3, there is a repairing process, but that changes the nature of the space enormously. So you can't really just call it repairing. But so for example, we can symmetrize a metric if it's not symmetric. Okay, 1 is a little bit more of an issue. We'll see it much later in this course. But for now, we want to have distance between x, y. For now, what I want to emphasize is the triangle inequality is the key. And why is it called the triangle inequality? Because it is simply the statement that if I have 3 points x, let me just draw the lines. Suppose I have a triangle, and then the ends of the points are the vertices of the triangle are x, y, and z. Then this distance here is distance of x, y. Here we have the distance between y, z, and this is the distance between x and z. In this case, xz wasn't even the longest side, but in general, the length of the side of a triangle is less than the sum of the lengths of the other two sides. So this is the key property that we use when we do when we study the geometry of spaces, but also when we study analysis. For example, let's just look at our first example. If I take x as real numbers, and then we look at distance between x and y, is mod of x minus y. Okay. Now verifying this as a distance is routine. If x is y, then this is 0, and otherwise this is positive. It's obviously symmetric by definition, and the triangle inequality can be obtained by checking cases. Okay. How about x equals r squared? We have 3 different important distances on it. Okay, so the L1, L2, and L infinity, and a whole bunch of things called LP, and various other things which are not any of these L's, but 3 particularly important ones. So let me call the corresponding distances D1, D2, and D infinity, because this usually refers to the size of a vector instead. So D1 of, if I took, let's not just stick to R2, but Rn, the same thing works in R2 as well. Rn is distance between, if I have a point x1, xn, and y1, yn. Well, we sum I equals 1 to n of the absolute values of xi minus yi. Now this is the yeah. So this is the sum of the distances in different directions, the earlier distances in different directions. It is routine to verify that it satisfies the property 3 as well by just considering coordinate wise, and by 1 and 2 are obvious. So here is d1, here is d2. Now d2 is the natural distance, and you can say it's Pythagoras theorem. Though formally you would use an inequality from Cauchy-Schwarz to say that this is satisfies the triangle inequality. The distance is, we look at the square root I equals 1 to n of xi minus yi the whole squared. Okay. So this is a little bit of an exercise to check that this satisfies the triangle inequality. Symmetry and the first property are quite obvious. If this is 0, then all these terms must be 0. So all xi's are yi's, and similarly symmetry is just from the formula. Triangle inequality is Pythagoras theorem effectively in higher dimensions, but by completing squares or Cauchy-Schwarz you can verify this formally. And the final example is of this set is, if I look at x1, x2, xn and y1, y2, yn, this is going to be sum I equals 1 to n of so previously you took up, I'm sorry, that was the infinity. Yeah, so that was the L1 distance. L infinity distance is, instead I look at the maximum of mod of xi minus yi. Okay, so this is for so I should spell it out as a set. I'll say maximum of mod xi minus yi. 1 is less than or equal to I is less than or equal to n. Okay. A little later we will verify that these are distances for those who have not seen metric spaces before. It is relatively routine, but if it is new to you, it is worth seeing this in detail. Right now we will simply define things and look at a few examples. Yeah, so these are the examples. So here we'll see the balls as well in these things. We'll come to that. So let me just make here a definition. Okay, so for X a metric space, and A in X, and R, let's say positive, we define open ball of radius R around A is the set of all points x in X such that distance between X and A is less than R. Okay, so this in the usual distance is just the open ball, and the closed ball BR bar of A is the set of all x in X. Distance between X and A is less than or equal to R. And a very good way to understand metric spaces is to understand the balls and also the sphere. So a sphere SR of A, so this is called the sphere, is the set of all x in X. Distance between XA equals R. Okay. So we have rapidly seen 3 examples. We have not justified that these examples are actually metric spaces. Simply said it was simple. 1 and 2 are really simple, but we should see these. But we'll understand these metric spaces a little better and look at these examples in it. But right now, before we get to those details, we'll look at another metric which is quite different in nature. This is called, this has various names. It's all, among them it's called the SNCF metric. This is named after the French national train service, because the fast trains, the TGVs, used to at least only connect Paris to the various cities. So the fast way to go to between one city and the other was often via Paris. So specifically, so this is a metric on R2. Okay. Again, we'll verify the metric properties in the next segment when we verify metric properties for the easier examples as well. But this is in some fundamental sense different from the others. It's not really metric on R2 even though those points are there. So let's take a specific point, which is the origin. There's an orange origin here. And what do I define the distance as? So let's draw some lines, and then I'll if we have a couple of lines. Oh, the point is this. So suppose we have a line. Sorry about that. I meant here it comes. So we look at all the radial directions from here. Okay, and let me draw the picture in 2 points, and then so we have 3 points here. Let's say this one, and this one. Okay, or perhaps it's confusing to have it like this, so let's add one more line and add a point, let's say here on this line. Okay, so what is the distance? Well, the idea is that the train service goes via Paris. So if you're lucky enough that your source and destination are in the same direction from Paris, the distance is the difference between these two. It's this much. But if you are unfortunate, so you simply go by this segment here, the orange segment joining these two. But if you are unfortunate and you are in two different directions, that is, you're here and here, then to go, you have to first go to Paris and then go back here. Okay, so what this tells you is that this is here's the distance and here's another distance. So we'll so this is the distance. Let me write these in polar coordinates. Okay, so suppose this is r1 theta 1. Now this is r2, but this is also theta 1. Okay, so theta 2, but theta 2 equals theta 1. Okay, now this is r3 theta 3, and this is r4 theta 4. So we define, well, the origin doesn't have polar coordinates, so a very special rule is to the origin. It's of course just mod r, the distance to r. So define distance between, let's cover all cases. Assuming symmetry, so I don't have to write them twice. So distance between any point xy and the origin is, oh, I'm sorry. So define, we'll use polar coordinates except at the origin, where we can't. So we'll have to have special cases. But you can see that you can condense this a little bit. For now, I'll write it out. Of course, distance between 0, 0 and 0, 0 is 0. It better be. Distance between a point r theta and 0, 0 is just the absolute value of r. Okay. Now, as I said, you can condense this because you can think of 0 as r being 0 and theta arbitrary, and you'll get 0 here no matter which theta you chose. And the same will hold in all other cases. Okay. So now, with the origin out of the way, the main points is if I take r theta and r prime theta, that is, we are in the same direction, or rather, let me write r1 theta 1 r and r2 theta 2 and split it into cases, equals, as I said, if theta 1 equals theta 2, you are in the same direction from the origin, so then it's just mod of r1 minus r2. And if theta 1 is not theta 2, then it's mod r1, the distance to the origin, plus mod r2. And the mod is unnecessary here. So this is R1 and this is just R2. Just because I had to use mod there, I use mod here as well. So it's the distance to the origin from each one added up to each other. So 2 points, even if they're very close in R2, they can become very far in the SNCF metric because you have to go back and come here. Okay, so this too we have to verify as a metric. It's a matter of checking cases. When we talk about topology associated to a metric, so though this is a metric on R2, we'll get a wrong topology, or we'll get a more interesting topology maybe in some ways, but not the important one that we actually have on R2. So we have introduced metric spaces and we have defined them. Our next step will be to slightly carefully verify, for those who have not seen metric spaces before, why the metric spaces we have are actually metrics.